Good day, everybody. Today I want to look at a result using Abel's theorem, which will enable us to find a given second-order differential equation. The purpose is I want to pick two linearly independent functions to start with and then find a second-order differential equation for which they will be the solution to. And I wasn't always sure that would be possible, but it is possible. We can see how to do that using Abel's theorem. So just a quick couple of preliminaries. If you have two functions, they're Wronskian, would be given by the determinant of first row of the two functions, second row, their derivatives, and take the determinant of that. So using the Wronskian, we have this nice result that if we have two solutions to a linear homogeneous second-order differential equation, and if the Wronskian of those two solutions is not zero, then those two solutions span the solution set. In other words, any other solution must be just some linear combination of those two functions. So that's a nice result. So here is Abel's theorem. One version, not the version I'll use. I want to look at it, but basically the second order differential equations in standard form. The Wronskian is given by the Wronskian at a t naught e to the negative integral from t naught to t. A more useful version for us is this alternate version of Abel's theorem. So if we have two solutions of the second order homogeneous differential equation, then the Wronskian is going to be, of those two solutions, must be some constant e to the negative antiderivative of p of t dt. Okay? So without even knowing the solutions, we know what their Wronskian is up to a multiplicative constant. Right? So just by looking at the second order differential equation, e to the negative antiderivative of this p of t term, the Wronskian of any two solutions is going to be some multiple of that. So that's what we'll use. So let's get down to business. So let's say I want to find a differential equation for which t and sine of t squared are solutions. Second order linear homogeneous differential equation. Well, what I'm going to do is I'm going to take the Wronskian, so the two functions and their derivatives, take that determinant, there we go. Then by that version of Abel's theorem, I know that the Wronskian must be some multiple of e to the negative p of t dt. So I'm going to use this to find p of t. All right, so we'll try and solve for p of t. We'll divide by the unknown constant. For a moment might seem like it's in the way, but everything will be okay. We'll take the natural log of both sides. So the log of e to a power will just be the power, and then the log of a fraction is the log of the numerator minus the log of the denominator. And now to get p of t, we'll differentiate both sides. So the derivative of this antiderivative will just give me negative p of t. And the derivative of the log, it's 1 over the argument times the derivative of the argument. So the derivative of the argument, you need the product rule here. You get 4t cosine t squared, and then plus the first derivative of the second. Derivative of the second will be negative sine of t squared times 2t. That gives me that. And the derivative of this term is right there. And then the derivative of this constant, well, it's 0. So it worked out for us. So P of t, let's see, we've got two similar terms. This first and third term combined to give me 2t cosine of t squared. And then for P of t, I'll just divide or multiply by the negative. So if I do that, then I actually get this minus the 2t. So there, that would be P of t. Okay, so now I know my differential equation should have been y double prime plus P of t y prime plus Q of t y equals 0. So now I know P of t. I'll put this in, and I'll go ahead and clear the denominator. So multiply through by this denominator. If I do that, then I get this, what was the denominator, but now it's this times y double prime, plus this was the numerator, times y prime. And now I need Q of t times the denominator, but Q of t is still unknown, so in the end, I still have this unknown function here, which I'll just call R of t. So the solution, the differential equation for which my two functions t and sine of t squared are solutions is going to be of this form. Let's solve for R of t so that one of them is a solution. So I can either choose the sine of t squared. It's a little more complicated. Let's choose the t to be a solution. In which case, y prime's 1, y double prime's 0. So if I substitute that in, then of course y double prime's 0, that's gone. Put in a 1 for y prime here. Got it right there. And then a t in for y equals 0. So I can solve for R of t. Just move this over. It would give me 2t cosine t squared minus 4t cubed sine of t squared, and then divide by t, and I get my R of t. So now I'll put this back into my ODE. So the R of t is what we just solved for. So if I put in that R of t, then what I now have is this quite long differential equation. So these were the same terms as before. There's what I get when I put in my R of t. And well, let's check the solutions. Y1 equals t works. That was forced. If you want to check it, it wouldn't be too hard. Y1 prime is 1, y double prime is 0 as before. So then that term's gone. If I put a 1 here and a t here, well, then all you have to do is distribute that t, and you'll see everything cancels to give you 0. So that was easy and obvious. But are we sure the other solution works? So let's check it. So y2 equals sine of t squared. Let's check that that works. So if y is sine of t squared, y prime's 2t cosine of t squared, and y double prime by the product rule, derivative of the first, second, times the second minus first derivative of the second, give me that. So if I sub it in, then I've got this times my y double prime, and then this, which is right there, times my y prime, and then this times my y is right here. So does that equal 0? Well, we're going to gather the like terms. So we'll start with the cosine squared terms. I've got 2 cosine times another 2t cosine, both of t squared. So that'll give me 4t squared cosine of t squared. And then there's one other place right here where I've got a cosine times a cosine, and that would be minus 4t squared. And those are the only two places where you'll get cosine squared. And now we'll check the sine squared terms. So I've got a sine times a sine here. That'll be plus 4t squared, which I got right there. And where else do we get a sine times sine? Over here. So sine times sine minus 4t squared. So again, so those will cancel. And then we've got a few sine times cosine terms. Sine times cosine, I've got a negative 2. I've got over here a plus 8t to the 4th. Oops. I've got that right there. I guess before that, I should have had over here. Let's see, plus 2. Yeah, right here, I've got a minus 8t to the 4th. sine times cosine. Then here's the plus, and then here's a plus 2. So all the terms, if you gather all the like terms, they look like that, and so it does equal 0. So y1 and y2 are both solutions of that differential equation. So we found it. So we found a second order differential equation for which the two functions I wanted to be solutions are solutions. Well, now let's jump to the general result. So in general, you give me the two functions, or I pick myself, whatever. Got two functions. We want them linearly independent. So if they're linearly independent, we can take the Wronskian. There's the Wronskian. Again, by Abel's theorem, the Wronskian has to be some multiple of e to the negative p of t dt in our differential equation. So again, just to solve for the p of t, divide by a constant, take the natural log of both sides, the log of the top minus the log of the bottom, differentiate both sides. So on the left, the derivative of this antiderivative will just be that negative p of t. On the right, derivative of a log, it's 1 over the argument. There we go. Times the derivative of the argument. So now I need the product rule. So the derivative of this argument, if I use the product rule, will be the derivative of the first times the second. It's y prime, y2 prime, y1 prime, y2 prime, plus the first derivative of the second. So it'll be y1, y2 double prime. Then minus, so if I differentiate this, I'll keep that minus factored out. Derivative of the first times the second, y2 prime, y1 prime, plus the first derivative of the second, y2, y1 double prime. And if you subtract, these two terms cancel. They're the similar terms. So we end up with p of t is this, y2, y1 double prime minus y1, y2 double prime, all over y1, y2 prime minus y2, y1 prime. So we'll sub into the differential equation standard form. We just found the p of t. So I'll put this into p of t, and again, I'll clear the denominator, so I'll multiply through by that denominator. So that'll give me this quantity y double prime plus this numerator y prime plus the denominator times q, again, some function we haven't determined yet, times y. Well, to find r, again, we want y1 to be a solution. So if y is y1, then y prime is y1 prime, and y double prime would be y1 double prime. Sub that into here. So I just get a y1 double prime, y1 prime, and a y1 into what I just had up above. And now we want to distribute and solve for r of t. So if I distribute, let's keep things in order of derivative. I have y1, y2 prime, y1 double prime, minus y2, y1 prime, y1 double prime. And if I distribute this to these terms, again, in order of derivative, it'll be y2, y1 prime, y1 double prime, minus y1, y1 prime, y2 double prime, then plus r of t, y1. Well, we've got a few cancellations here. This cancels with that. And so solving for r of t, I mean, we'll move these two terms over. So move this term to the right-hand side. And then we're going to divide by y1. So this y1 cancels. So I have y1, y2 double prime. And if I move this term over and divide by y1, that's my r of t. So now if I substitute that into what I had before, again, these were the same as what we had before. There's the r of t. This is the general formula. So there it is. And of course, I'll check that y2 was also a solution. Y1 was obviously forced to be a solution, but let's check y2 is as well. So if y is y2, then y prime is y2 prime, and double prime is y2 double prime. So I'll just sub that in. And if we now distribute, we'll get this term minus this term, easily seen by distributing. Distribute the y2 prime, get this minus this, and now distribute the y2. Again, I have everything in order of derivatives. So let's check what happens. So this term will cancel with this term. This term will cancel with this term. And then lastly, this term will cancel with that term. So y2 is also a solution. So this is our result. You give me two linearly independent functions, and I can construct a second order differential equation for which they will be the solutions. The two functions have to have a continuous second order derivative as well. So finally, just to look at some examples. Here's the one we've already gone through. We did this one first. So if I want these two functions to be a solution of a second order differential equation, this will be the second order differential equation. If I want t cubed and e to the 2t to be the solutions, this is what would result. And again, some simplifying was also done. Sometimes there's like a common factor of t, or maybe e to the 2t. That could be, if it was in every term, you could factor it out and discard it. So this is the simplified second order differential equation. And you can check both y1 and y2 are solutions, and any other solution can only be from linear combinations of these two. Again, t and e to the negative t squared. This differential equation would have these two as solutions. And lastly, for root t and cosine t, this differential equation, y1 and y2 here are solutions. And that's the span of the solutions. There can be no other solutions other than linear combinations of those two. So I thought it was a neat result. You know, if you give me any two functions, as long as they have a second derivative, then yes, I can make a differential equation for which they will be solutions. So I used Abel's theorem to do this, and afterwards, I then decided to look up the result, and it took a while, but I did finally see that, of course, it is a known result, and actually a nice way to describe it is, you know, the y1 and y2 are provided, like t and e to the 2t, or whatever. So you give me the two functions. If you take the Wronskian of those two functions, but with y, and set that equal to 0, that would be the differential equation. In other words, this would be something like, so if you do y1, y2, y, and then y1 prime, y2 prime, y prime, y1 double prime, y2 double prime, y double prime. So if you take this determinant and put that equal to 0, you're going to get the exact same thing that I had, namely this. And this can then be generalized to, if you want if you give me three functions, then I could find a third order. So you can just keep increasing the number of functions, then you increase, you know, to get a square matrix. For example, y1, y2, y3, y, put it equal to 0. So that's the general result, which is, of course, known, but not too well known. All right, so hope you enjoyed that. Thanks, and have a good day.